speaker from the University of Wisconsin, CS department for today's talk. The speaker, Dr. Hanna, actually was a student here 10, 12 years ago.
Yeah.
12 years ago. He got his PhD from the University of Texas CS department. Before that, he was a student here, exactly here. Actually, he took a course from CS 375. So we're very glad to have Dr. Hanna here. Before as a student, now as a cop. And the talk that he will be giving, we don't have any speech talking about things in this area, so that it will be very interesting for us to hear a talk in this direction. Okay, and I hope that you said, as you have indicated, that you would briefly talk about your history. All right, so let's welcome Dr. Hanna from the University of Wisconsin, Madison campus, CS department.
Thank you. Thank you very much for the introduction. It's really great to be back here, where I spent a lot of time in this building as an undergraduate student. So, and also thank you for accommodating the unusual talk time to do this on a Friday. So thank you very much. So we see that children and animals, they learn from experience. Children, they start learning to crawl, and then they learn to walk, and then they learn to run before you know it. Now you can program robots to walk. People have figured out like the physics of doing this, and you can program a robot to do it. But no matter how many times a robot walks back and forth, it won't get any faster or more capable. So in my research, I aim to develop the algorithms which enable robots and computers to learn from their experience, such that they can become even more capable than we can program them. So in this instance, this is showing a robot. We developed the fastest walk ever on this now robot using a type of machine learning algorithm. In general, my research focuses on developing the algorithms that enable computers and robots to exhibit the same adaptive and flexible goal-directed behavior that we observe in people and animals. And so I'm going to talk about some of the recent work that my group is doing in this space here. But before doing that, Frank asked me to just say, to spend a couple of minutes just talking about how I started at the University of Kentucky and now have ended up as an assistant professor at the University of Wisconsin. So right, as mentioned, I did my bachelor's here at Kentucky, studying computer science and math. I started in 2010 and graduated in 2014. And I was actually, before I even knew I was coming here, I was thinking this past year about like, why did I ever get into artificial intelligence, and what made me like, so interested in like how we can develop algorithms which enable people and animals to act similar to how people do. And so in thinking about this, I traced this back to one lecture. I was in Dr. Calvert's CS 100 class, but this is actually, we had one lecture where Dr. Goldsmith came, and I may be not remembering this question right, so I'm kind of paraphrasing it, but she posed to like a bunch of first semester freshmen in computer science, how can algorithms enable decision making and learning? Like, how can algorithms enable intelligence? And at that time, I was like learning to program. I knew that like, okay, we specify exactly to a computer what to do. Like computers by themselves, they're very dumb. So you write code which says step by step, this is how you carry out some computation. And so the idea that this same kind of reasoning could be applied to intelligence was just fascinating to me. And I had no idea how to do it, but it was just very interesting. And so a bit later, as a freshman, I started undergraduate research with Dr. Goldsmith. And so my undergraduate research focused on sequential decision-making under uncertainty. And so I had a lot of, this was just a really fascinating topic to get into artificial intelligence on. And it was the first time where I encountered that we could write out mathematical models to kind of describe an intelligent agent interacting with its world. So after spending some time in doing undergraduate research here at Kentucky, I then did my PhD at the University of Texas at Austin. And towards the end of undergraduate, I began getting very interested in machine learning, because I always found this very interesting. You program a computer exactly what to do. How can it get better with experience? How can it surpass what you can program it to do? And so kind of putting together both my undergraduate research and this interest in machine learning, this led me to the area of reinforcement learning, which if you're not that familiar with machine learning, reinforcement learning is the branch of machine learning which focuses on learning through interaction. So take it where you model an intelligent agent which takes actions, figures out the actions which lead to successfully reaching a goal, and then how to kind of continue taking those actions more in the future. And I also do work in robotics as one kind of primary application area. Following my time as a PhD student at Texas, I then did a postdoc at the University of Edinburgh in Scotland. I also spent time there as a research consultant at 5AI, which was a startup in the self-driving vehicle industry. And then finally ended up at University of Wisconsin, where I'm now an assistant professor. And I'm kind of continuing to expand these research directions that have really started a long time ago when I was an undergraduate here at Kentucky. So. The area that I specialize in is called reinforcement learning, and reinforcement learning models an intelligent agent interacting with kind of an unknown environment. And this is an incredibly general paradigm because so many problems in our world are fundamentally sequential decision-making problems. So reinforcement learning has had a lot of kind of notable breakthroughs and cool applications in the past decade. So one that actually happened very early was superhuman performance at video game playing, where you could have one agent learn to play all these video games at or above human level. In 2016, a computer defeated a human Go player for the first time, a system largely based upon reinforcement learning techniques. This was a game which was considered maybe it was going to be decades before a computer would be able to defeat a human, and it happened much sooner than was expected. Another cool recent application, control of nuclear fusion. There's some very challenging control problems involved with shaping these plasmas in fusion reactors, and reinforcement learning has been successfully applied there. Any company doing web marketing uses reinforcement learning to optimize how ads are shown to you. So if you're ever having trouble putting down a social media app, it may be because of reinforcement learning. Control of infrastructure, such as cooling in data centers, is another place where reinforcement learning has been applied. And as one more instance, kind of everyone's favorite new AI application, ChatGPT, while largely based upon language modeling techniques, in order to go from a large language model to a chatbot that a company will feel comfortable putting in front of people, reinforcement learning techniques are crucial for fine-tuning its behavior. So while all these applications are very diverse, they can all be modeled as sequential decision-making problems, where you have an intelligent agent interacting with a black box environment, where the agent initially doesn't know anything about the environment, but it has an interface that it can interact with the environment. And that interface is as follows. At any moment in time, the environment is in some state. The agent observes the state of the world and then selects an action in response to that state. The action then is passed to the environment, and the environment responds by transitioning into a new state and generating a reward for the agent. So we say that the agent's behavior is formalized as a policy, which is a mapping we usually denote as pi, which just maps the state to some method of selecting actions. If you want to be a bit more formal, we say that there's a probabilistic transition function where we have some probability distribution over possible next states we could see given the current state and action. And the reward function is also a random variable depending on the state and action. Interaction in this model proceeds as follows. The system is in some state initially. The agent takes an action, receives a reward. The environment transitions to a next state, and then interaction continues. So this modeling an agent interacting with its environment in this way, it kind of imposes this trade-off between short-term benefit and long-term gain. The agent may take an action which gives it an immediate good reward, but that eventually leads it to not getting very much reward in the future. On the other hand, maybe the agent takes a different action, which leads to a suboptimal immediate reward, but the opportunity to achieve much more reward in the future. So we denote this entire sequence of interaction as a trajectory. And the goal in reinforcement learning is to find a policy which will maximize the expected sum of future rewards that the agent can receive as it acts. As one other callback to my time at Kentucky, this model here is called a Markov decision process. This is what I did a lot of my undergrad research on, was methods for these models. This paper that I've linked at the bottom, Decision Theoretic Planning from Craig Boutillier, was known kind of lovingly as the monster paper in Dr. Goldsmith's research group. And I think one of the first things I did as an undergrad was she said, read this paper. And I don't think I got very much out of it because I just didn't have the background. But I was, again, like fascinated that one could like actually write out a formal model of intelligent acting in an environment. So, okay. So in my research, what I like to do is I like to try to find problems which are hard for reinforcement learning algorithms, but where it seems like there's promise for reinforcement learning as a solution. And then look at these, like what are the fundamental challenges which make it so that RL cannot be applied in them, and then try to address those at a more general fundamental level, which is going to be applicable to many different applications. So I'm going to talk about one challenge problem, one test bed that we use in my lab today, but this is just one instance of problems that I work on. And this is the test bed of robot soccer. So robot soccer is a test bed in the robotics literature. There's been, for decades now, people have been trying to develop robots which are more and more capable of soccer, with the goal being, if we can get robots that can play soccer well, we can get them to do very many other very useful things in the world. It may seem like, since people kind of naturally, we learn to play soccer, if you're a soccer player, why can't we get algorithms that can also enable robots to just learn instead of needing to be manually programmed here? So I'm going to talk a bit about my lab's work on this problem to start off the talk. So let's just talk about soccer as far as people play it to start here. So if you're not familiar with, or you haven't heard of the RoboCup Federation before, RoboCup is an international organization where every year there's an annual competition which involves a bunch of different robots playing soccer competitions with the goal to drive basic robotics research. It's been around for a couple of decades now, and the mission statement of RoboCup is that by the middle of the 21st century, a team of fully autonomous humanoid robots will be able to play a game against the FIFA World Cup champions, and the robots will be able to win. So if you think about how in AI research we've seen things like a computer can beat a human in chess, a computer can beat a human in Go, this is like a substantially more significant challenge to actually beat a human in a game in the physical world where we really excel compared to computers. And if you try to break down everything that an intelligent agent has to do in soccer, it's really quite amazing that people can do this task. So you have, first of all, just the problem of controlling a robot in the physical world and doing that in a really dynamic way. So running, kicking, jumping, all of these skills are even difficult to develop in robots today. And that's just one robot by itself in the lab. These skills have to be robust enough when you have adversaries who are trying to actually make you fail at what you're doing at the same time. There's challenges in terms of coordination and teamwork. So players don't play in isolation. They have both adversaries they must overcome and also teammates they can leverage if they can properly coordinate. And then all of the decision making has to be happening in real time. So if you think about chess, you can stop and you can think about your move for a time. You can do the same thing in Go. But in soccer, if you stop and think for too long, the other team just comes and takes the ball from you. So you have to have really real-time decision-making here. But if you're kind of thinking, well, this is just a game, why do we care about robots that can play a game? I mean, there are also kind of real things we want intelligent agents to be able to do, which involve real-time decision-making in multi-agent environments where maybe some agents behave adversarially compared to you. So I think by pushing the research and pushing robots to be able to perform a task like soccer, the goal is that this will advance all sorts of other applications as well. So how do you approach this? This is the robot that we work on in my lab. So this is not a robot that will be playing against people anytime soon because it's much smaller, but some of the intelligence challenges are still the same. This is the Now robot. It's a humanoid robot which stands about this tall on your leg. And the traditional approach to using this robot in soccer is to build a classical robotics stack. And this is how people have been designing robotic systems for a long time now. So in a kind of the classical robotic stack, that now has some sensors, in this case cameras, where it takes input. It's like getting information about the world. You run a perception algorithm, so for instance, a deep neural network, to extract information like where is the ball, where are other robots. The robot kind of integrates information over time to construct a belief about what it thinks the state of the world is. And then kind of in the middle here, this is where a person is going to craft some rules about how to behave in this task given the current state of the world. So you might say, I see the ball, it's over there, so like let me write a function which tells the robot to walk to the ball. And then this kind of higher level behavior gets eventually mapped all the way down to motor commands which make the robot move and do things like kick or walk. So what my group has been looking at is, well, this rule-based behavior is very difficult to specify in complex multi-agent tasks. So can we just replace the rule-based behavior with a neural network that we're going to train with reinforcement learning and do this such that the robot is just as capable as if we had put in all the effort to manually program the robot. So the way we do this is it's very difficult to actually train directly on a physical robot. I'm going to talk a bit more about why that is in a little bit, but our approach so far has been that we developed a simulation of the robot's environment. The robot just trains, it learns by practicing to score goals in the simulated environment. And after it's done this for a long time, we take the resulting learned behavior, put it on the physical robot, and find that it's successful. And we've developed methods to be able to do that. This has been following a line of work that I started during my PhD. But this is one really nice thing in our current work is that because we're only focusing on like one piece of the robotic stack, we can simulate the robot at a very high level of abstraction. So our simulator here is just really modeling this kind of high-level notion of like the robot as a circle needing to like learn to approach the ball and carefully nudge it into the goal. And this works. So this works quite well. So we participated in the RoboCup competition for the first time this past summer, and we participated in a division of newer teams, but actually finished third overall in the competition, where we were the first team to actually really base their behavior entirely on learning instead of kind of manually specify the behavior there for this the competition we were a part of. So this is an instance of us scoring. In this case, the other team, their robots, they were having some technical trouble, so we got an open, kind of clear path to the goal. But this is like, so no one like programmed this robot how to approach the ball to move it. It just figured out over time that it would achieve more and more reward as long as it moved the ball and got it into the goal. It's kind of a bit more multi-agent instance. This is a quick video of our robot kicking and the other goalie diving a little bit too late to get after it. Batteries died because it's. Oh. I can. No? Great, thank you. Hello. All right. Good. So in my research, we try to think about like, well, what are the general challenges here? Like, not just like, cool, we can get a robot to play soccer, but like, what are the problems that made it hard to apply this in soccer? And if we tackle those problems, is this going to make reinforcement learning much more applicable to many more applications? And so this is just a general philosophy. Part of my research philosophy is that these challenging use cases will motivate kind of fundamental research advancements. So challenge one that you see with robot soccer, I already told you, we can't actually learn on the real robot. So the robot is learning in a simulation which is not like it's a low fidelity representation of the robot's reality. And we would ideally be learning directly on the robots, just as how people really learn from their own experience. And so this research challenge one is that reinforcement learning algorithms, today's kind of state-of-the-art methods, are too data inefficient to be able to actually do training on a real robot. And by data inefficient, I mean the robot has to learn for a very long time to learn something useful. And so that's why simulation is nice, because in simulation you can run your simulator faster than real time, and even if your algorithm takes a long time to converge to good behavior, you don't care because you can just do this faster than real time. But on a physical robot, everything must be real time, and so we need more data efficient algorithms. So that's the first thing I'm going to talk about in the talk today, is how we've kind of thought about rethinking the problem of exploration in reinforcement learning to produce more data efficient learning. And then the second research challenge, which I will talk about at a kind of more high level at the end, is that being able to validate when a learned behavior is going to actually be performant when deployed. So this is kind of roughly in the space of like AI safety to some extent. Like, how do we just know before we've ever deployed a behavior that it's going to, won't lead to some really poor outcomes? And I'll talk about some recent work that we've done on like scaling what's called offline evaluation of learned behaviors. So starting to talk first about data efficient learning. So if you want to apply reinforcement learning to a new problem, one of the de facto choices that many people use is a type of method called on-policy learning. And on-policy learning works as follows. You first have you let your agent, it has a current policy, which is initially not very good. Under the current policy, the agent interacts with its world for a while and sees how its actions are leading it to different rewards and how they affect the states that it visits. Then after doing this for some time, you have a method for updating the policy to move towards a better policy using your experience. And then all of the experience the robot has so far is discarded, and the robot repeats this process. It has to collect a whole new batch of experience and then perform another update. And if you just kind of iterate this procedure, eventually you'll get to a well-performing policy. So this is the basis of like the types of algorithms which are used on ChatGPT for fine-tuning as well, is just to iterate, collecting data, updating the policy, throwing out the data, collecting more data, and continuing. So in what's called on-policy policy gradient learning, the typical means of doing this is to say that our policy is represented as a differentiable function, which maps states to a probability distribution over actions. So if you want one instance of this to think about, this could be an artificial neural network. And the policy is differentiable with respect to some parameters that it has. And we want to learn the best setting of these parameters that give best performance. So if the policy is a neural network, the parameters would be the weights on the connections of between neurons. And so policy gradient methods optimize the parameters of a policy using gradient descent. So a fairly simple optimization method is used here. If you're not familiar with gradient ascent, the kind of basic idea is that we have an objective function. If you imagine compressing the space of all a policy is a high-dimensional object, but if you were to compress that down into just a single dimension and plotted that along the horizontal axis here with gradient descent, maybe this is our current policy, we estimate a direction which is going to improve our objective. We then take a step along that objective and we move to a new policy. So this is what kind of this de facto, like the kind of one of the best ways you can apply reinforcement learning, how it's doing it, is just doing gradient descent on an objective. So I'm going to talk, you can ignore the exact expression here. I'll explain a bit more intuitively what this means, but policy gradient methods optimize the policy with according to the following gradient. And to say what each part of this means, so this last term, gradient of the action log likelihood, this just says push up the probability of this action. This term here is called the advantage, which just says this action, if I switched my policy to take this action more, how much more reward would I achieve? So this together, this is saying I want to increase the probability of actions which lead to good reward and decrease the probability of actions which lead to poor reward. And then finally, this is a weighted expression. This is actually an expectation over states and actions which will be visited under the current policy. So that's what the expression means. And what we want to actually do, though, in policy gradient learning is we want to estimate this. Because you don't actually, in practice for real problems, you'll never be able to actually exactly know these quantities. So you estimate them instead, typically using a Monte Carlo sample approximation. So again, this looks like this, where we're going to run our policy for m time steps in our environment, and then just take an average of the resulting advantage multiplied by the gradient log likelihood. And so this gives us a direction which tells us how to change the parameters of our policy to move towards a better policy. Now, this is a Monte Carlo estimate is a very statistically sound method of approximating the gradient. If you make m large enough, this approximation converges to the exact gradient, and you're updating your policy in the right direction. But really, for data-efficient learning, we're never going to have m going to infinity. We have to work with a finite m. So there's going to be some approximation error in this gradient, which means that we're not quite updating our policy in the right direction. I'm going to show one instance where we found that this actually really does impact learning, can make these algorithms suboptimally converge. So this is a simple example of training a simulated character. You can think of this as like a simulated robot to swim across the ground. So this is kind of like a snake-like robot. And there's, while there's very many different policies which can be implemented, you can kind of categorize types of learned behaviors as follows. So the first one is just random wiggling. This isn't a successful motion at all. The robot is just kind of like squirming around and not making any progress. There's also this behavior which we call slow swimming, although it's actually a bit more of just kind of jumping forward and then sliding to a stop. And this isn't really successful, but it's better than just randomly wiggling. And then you kind of have like a more swimming-like motion where this robot is like learned to like kind of extend out and then kick back, extend out and kick back, and this causes it to make forward progress across the ground. So what we have at the bottom is optimal behavior. The top is the worst case, and then this middle is like a suboptimal behavior that we don't want to converge to. However, it turns out if you take a state-of-the-art on-policy algorithm and you run it 100 separate times on this problem, you'll see that it can learn the optimal behavior, but actually about 50% of the time it fails to converge to that optimal behavior. Because it's using these only approximate gradient estimates to update its policy parameters, what ends up happening is that about 50% of the time the robot converges suboptimally to a behavior which isn't very good. To break this example down just a little further, I'm going to kind of further simplify it and just say that we have kind of 3 possible outcomes in terms of what the robot's behavior could generate, either fast swimming, slow swimming, or random wiggling, and that there's only 2 actions that the robot can take. Now, this is a gross simplification because it's actually controlling itself at like the motor level, so its action space is much larger. We're saying that like it has 2 choices at each time step. Either it stretches itself out or it kicks back. And ideally, like the optimal policy should like alternate these 2 behaviors to swim forward. So these are the 2 options, and so I'm drawing like a simplified representation of the agent's decision-making process here, where it chooses to either stretch or kick back at every moment in time. If the robot is able to kind of string together alternating behaviors, it leads to fast swimming. If it only kicks back and doesn't first stretch out, it'll do slow swimming, and otherwise we get random wiggling. Now, and this is just showing the total reward that will be received. So best is fast swimming. And under the agent's initial policy, when we kind of initialize a neural network randomly and let that be the agent's first initial policy, the probability of ending up with this fast swimming behavior is very small. It's maybe like only 1 out of 100 trajectories leads to fast swimming. Where it's very easy, a lot of the trajectories will lead to just random wiggling because the agent doesn't know anything. And about 50% of the time it'll make some progress forward, but in a suboptimal way. And what this ends up doing is that when we just use an approximate gradient, it turns out that we don't often see this fast swimming outcome at all. And the approximate gradient tells us, well, increase the probability of the slow swimming actions because they look best to me here. And since they look best, the agent ends up converging to the slow swimming behavior, but more just because it's never seen this fast swimming behavior at all. So we call this method of exploration, where you just kind of randomly follow the policy by sampling actions according to its current probability distribution. We call this on-policy sampling. And in on-policy sampling, any trajectory which has a low probability is going to tend to be undersampled. So the agent very rarely sees this optimal behavior, and this causes the policy gradient to push the agent towards learning suboptimal behaviors. But our observation from this is that if we're not seeing the successful behavior enough to know to increase its probability, what if we just explored in a different direction? What if instead we performed adaptive sampling, where any time there was some trajectory which had high reward, we wanted to increase its probability to make sure that it was properly represented in the data. In fact, we just want to make sure that the agent experiences kind of all possible outcomes. It has like a more diverse exploration, which will lead it to discovering these high rewarding events. So the intuition is that we would like to always kind of be pushing up actions which are undersampled in the data. To illustrate this point a bit more about what we mean by undersampled here, suppose in just one state, our current policy put equal probability on two actions, either action A or action B. If we just generate behavior by sampling from our policy, then you might end up with some experience which looks like this. So what this figure is showing is our expected frequency is that we would see each action 5 times if we visit one state 10 times. But if you're just sampling from the policy, there's going to be some variation in a finite sample. So after 10 visits to the state, you may end up with something like 8 of one action and 2 of the other. So in this case, we would say that action B is undersampled relative to what we would expect it to be. On the other hand, you could implement a different kind of decision-making rule where the agent always tries to take the action which is currently undersampled. And this looks something like this, where the agent just alternates. Every time it visits the state, it says what action is the most undersampled, and then I take that action. And then that leads, after 10 visits, to data occurring at exactly its expected frequency if you use this decision-making rule. So we call this sampling error when the data that we get does not match the desired proportion under the current policy. And what we can see in this example is that adaptive sampling could actually produce data which has lower sampling error. In fact, we can exactly match our target frequency, whereas with just random sampling, as is typically used in on-policy methods, we have some amount of error. So we developed a new kind of exploration method for reinforcement learning in on-policy algorithms, where now instead of just updating how the target policy, we also maintain a separate policy whose only job is to provide data for optimizing the policy we want to learn. So we call this a behavior policy. And again, we're not really trying to make this behavior policy the best possible policy. We just want it to be good at exploring and producing new data for us. The target policy here is the policy that we want to be as good as possible. So the behavior policy produces data to optimize the target policy. So in our new procedure, instead of just iterating between following our current policy and optimizing the current policy, we're now following this behavior policy to produce data, kind of iteratively updating the behavior policy to make sure that underrepresented trajectories have more probability, and then iterating back and forth to produce a good set of data that we then use to update the target policy with a more accurate gradient estimate. And so what we're doing is we're adjusting the behavior policy kind of at every step to produce trajectories that are going to be properly represented under the target policy. So the key technical challenge with this approach is how do you know what trajectories are currently undersampled with respect to the policy? And so we do this instead by looking at what actions are currently undersampled. So the intuition for what we want to do is that the behavior policy should increase the probability of actions which are undersampled with respect to the target policy. One way of measuring this is you can estimate what's called the empirical policy. You can think of this as we're counting up the number of times that an action has been taken in each state. And if the probability of some action under the current policy is greater than its empirical frequency, that means that the action is undersampled and we should increase its probability. There is a problem here. While this is an intuitive idea, the challenge is that actually tracking this empirical policy is kind of computationally hard during learning. And I mean that more in not a real like computational hardness sense, but more just like it's a difficult optimization problem that you would have to run as an inner loop here. So to overcome this, one student that I worked with developed a really useful heuristic, which involved not actually tracking how often each action has been taken in each state. And so the insight here was just that the gradient of the log likelihood, so this is kind of like our policy gradient, but we're ignoring the advantage term in here. So this is the same kind of loss function which is used for supervised learning instance here. So when you look at the gradient of the log likelihood, it specifies an update direction where for any action which is kind of oversampled relative to the current policy, it says increase its probability, which is actually the opposite of what we want to do. We want to be increasing the probability of undersampled actions. So fortunately, if we just take a step of gradient descent instead of gradient ascent, then we end up getting exactly the kind of update we want for our behavior policy. And this is going to then increase the probability of undersampled actions, which will increase the probability of undersampled trajectories overall. So this is just a heuristic. It's not like this isn't actually a loss function we're optimizing, but a heuristic that you can take to increase these probabilities. But there is actually some nice kind of theoretical results about how this compares to just random sampling. So I won't go into all of the details of this, but this is just to say we have some measure of sampling error in our data, meaning how much the actual data distribution matches its expected distribution. And what we can say is that under our new method, which we call robust on-policy sampling, this error is bounded in probability with a term which decreases much faster than just the standard way of decreasing, the standard way of taking data. So we're going to integrate this new way of updating the behavior policy into an algorithm called proximal policy optimization, which is a state-of-the-art reinforcement learning algorithm. And we integrate it kind of as follows, where at the first iteration, we have our current policy, which maybe for some state takes like different actions with 50-50 probability. Sorry, this is first showing is like this is the baseline here. This is like what a vanilla policy gradient method does. If the current policy takes these actions with 50-50 probability, the data collection policy is the same as the current policy. We sample from it. There'll be some finite sampling variation. And then at the next iteration, we have to discard our data and collect a whole new sample where now we've updated our current policy to maybe favor action B. We again sample from it with the same policy, and we get this data. With our new approach, what we do, the first iteration looks the same, but then as we move to the next iteration, we keep our old data, and then we just update our data collection policy to push up the probability of whatever action is currently undersampled with respect to that current policy, and then collect additional data. And this procedure is going to, it does two things. Overall, though, it gives us a better approximation of our gradient, but it does this by correcting sampling error and also simultaneously reusing data from previous iterations. If you're kind of more familiar with reinforcement learning, there's some categorization in RL of off-policy versus on-policy algorithms. And what's really interesting for the RL audience would be that props is an off-policy algorithm, but it generates data that's more on-policy. If that doesn't mean a whole lot to you, really kind of the key thing is that there's this fundamental classification of different kinds of RL algorithms, and we're introducing a method which blurs that boundary. And we've said kind of calls into question if it's the right distinction to be making in the first place. So with that, I'm going to show some empirical results just to show how the method performs. So the way to interpret these plots is that on the horizontal axis here, I'm showing learning time. And on the vertical axis, I'm showing a measure of performance, specifically the interquartile mean of different learning trials. So what you want is you want a method which kind of gets as high as possible with not too much experience. So this will be your basic, this is proximal policy optimization, which is the same algorithm used in ChatGPT and other RL applications. This is another baseline. But kind of importantly, with our adaptive sampling procedure, we're getting we're converging to a higher level of performance with less data. So in some cases, we even we cut the time in half in order to be able to reach a high level of performance. these are the kind of standard results that you see in a lot of reinforcement learning papers or learning curves like this, which show just like how fast you're reaching different levels of performance. But actually what we were kind of most excited about was a different set of results, which shows the robustness of these learning methods. So if you recall earlier, I told you that on this one toy problem, that about 50% of the time, the state-of-the-art algorithm converges suboptimally. So it's not, the previous results were showing that on average it does pretty well. What we're saying here is that, well, if you just ran that algorithm, you have a 50% chance that you'll get a suboptimal outcome with it, and you might have to rerun it to get a better behavior. So these performance profiles that I'm going to show, the way to interpret them, along the horizontal axis is a performance level, and along the vertical axis is the fraction of independent runs which reached that level. And so this is, again, is PPO, this kind of widely used algorithm, and what you want to see, this dashed line corresponds to median performance. And so the median performance is often less than what the mean performance will be. And so with our new approach, we're pushing out that median performance more, which means if you run this algorithm, you have an increasingly better chance of getting high performance. So this swimmer domain here, this is the example I showed earlier. You can see whereas PPO is kind of 50% of the time it converges to this suboptimal level, our method is getting about, it's about like 75% of its runs reach that level, I think so. So really this kind of robust performance is like very important, because if you run your algorithm on a robot and it converges suboptimally, well, you would just have to kind of rerun it, the only thing you could do. So we really want algorithms which every time you run them, they lead to the optimal performance. Okay, so this is a new line of work that I'm very excited about. It's a new type of exploration for RL, and it's what I would call exploration for statistical efficiency. Whereas kind of classically RL is thought about exploration is that we're trying to just uncover new experiences. We're focusing on statistical efficiency. And this raises new questions about how you integrate our methods with kind of the classical view of exploration in RL. There's also some implications for wider areas of reinforcement learning, and so we're currently investigating coordination and multi-agent learning as one potential new direction. But the main takeaways from this part are that many RL algorithms rely on approximating gradients for learning. Better approximation of those gradients equals better learning. And so we've introduced an algorithm that we call props, which is a scalable method for kind of more data-efficient estimation of gradients. So I have just a little bit more that I'm going to talk about one other area at a slightly higher level, our work on trying to make sure that AI systems are kind of safe for deployment, and that we can have confidence in their performance before we deploy them. So I'm going to go over this at a kind of slightly less technical level than I did in the previous part, just to give you a bit of a sense of some of the problems my lab is working on. So in this part, our goal is that we would like to predict the learned behavior of an agent before it's actually deployed. So I wanted to give one example. This is from the RoboCup competition this summer. At the competition, we're like kind of making all sorts of tweaks to our behavior, and then we're deploying it in games. And we might like to say, when we make a change, how is this going to affect some notion of performance? And what we do see, we don't have methods for this problem. So what we see is that sometimes we get undesirable outcomes. Like here's a video of our robot just bowling another team's robot over, and it's a kind of a very short clip there. I'll show that one more time, but we kind of had a bit of a problem with our robots being too aggressive. We would have liked to have detected that before we deployed them, instead of having to test at game time. So this is the big question. Can we determine the expected performance of an agent before it is deployed? And our goal is that we would like to be able to do this with historical data that has been collected by deploying other agents in the world, so that we can actually evaluate an agent before ever deploying it. I'm going to skip, in the interest of time, I'll skip over the formal definition, but what we're really looking at here is the on average reward that a policy accrues. This is just one instance of what you might, how you might capture desirable behavior. So this is not, AI safety is an incredibly broad field, so I mean to say that we are looking at one piece of that here This challenge of offline evaluation is that we're given a policy that we would like to evaluate and predict what will its average reward be when it is deployed. We have access to a data set of previous interactions where this data set has the following form. We have a bunch of instances of environment state, the action which was selected there by some other agent, what the resulting reward was, and what next state resulted. The key challenge is that the given policy that we want to evaluate is different than the policy which collected this data, policy or policies which collected the data. And our goal is that we want to use this data to just evaluate this policy that we want to evaluate. If we were able to run the policy that we want to evaluate, just imagine that we would just run it in the environment. We would observe it for some time. We would see the reward that it obtained. And then we can estimate its expected performance as just the average reward obtained. So our estimate would be, again, like a Monte Carlo approximation, taking the mean reward. Very good statistical theory on the properties of this estimate converging to what we're trying to estimate. The kind of key challenge now in the offline challenge is that decisions in the past were made by a different policy, which is inducing a counterfactual question. It's saying, what if in the past I had been deploying my new policy, which I haven't seen yet, what would have the outcome been if I had done that instead? Or in a kind of slightly more technical level, we have a distribution shift, where now actions are taken according to some other policy. And this change in data collection means that our just simply averaging rewards does not give us a valid estimate of the performance of our new policy. So there's been a lot of work, which I won't go into, on addressing this challenge, and a lot of methods developed for it. But nevertheless, recent benchmarking efforts have shown that these methods fail to evaluate untested policies in challenging problems. And one way in which they fail that we're really focusing on in my group right now is that seemingly irrelevant differences between policies can distract offline evaluation. So I'm going to give one kind of very simple, a bit contrived example of this. So imagine that we had this quadruped simulated character here, and it was walking across the room, and we wanted to evaluate performance of some policy for this quadruped in navigating a maze, like how long it would take to get through the maze. And let's say that in this agent, our data was collected by following a policy that always stepped with the left foot first, but now we want to evaluate a policy which always steps with the right foot first when it begins walking. This is enough of a difference that it would kind of completely throw off some of the state-of-the-art methods for offline evaluation. But I think we look at this and we say, that's not important for traversing the maze. That's an irrelevant detail here. So our work in this space has been trying to filter out irrelevant differences, how to identify them, and filter them out for better offline evaluation. I'm coming up on the end of the time, so I won't, and wasn't really planning on going into the details of how we do that. But this is a new direction for scaling offline evaluation through a notion of abstraction. And so kind of the key takeaway is that we're seeing a lot of promise in this direction. Kind of filtering out irrelevant differences, we get more accurate estimates of untested policies. And so this is some recent work. This is at AAAI this year, where we're seeing is on the vertical axis the error we get in predicting policy performance, and that with our methods which abstract away of relevant differences, we get more accurate prediction there. We have some follow-on work that will be published at NeurIPS in December, where we're doing this, but we're actually learning irrelevant differences as well, and again, getting more accurate evaluation. So there's a lot of, this is the beginning of what I think is a very promising line of work for better evaluation of untested policies, but we're just scratching the surface of using abstraction to scale these methods. I'll skip over that just to get to questions, but so just in summary, the goal of our work is to identify these fundamental challenges that challenge the application of reinforcement learning algorithm, tackle those at a general level, and in doing so, make reinforcement learning more broadly applicable for everyone to use. So in this talk, I've talked about two general research challenges, one, needing data-efficient RL algorithms, and two, being able to predict that learned behaviors will actually be performant enough to be deployed on real systems. and presented some of our work in addressing these challenges. Finally, just to conclude, I want to acknowledge students and collaborators who have done a lot of work in this space. There's other people, this is just students who've done work that was talked about in here. There's very many other people that I'm very grateful for as well. And with that, I will conclude, and I would be happy to take questions now. And thank you all once again for coming to the talk. And please feel free to get in touch if you have to run off, since we're coming up on the hour.
As Kevin said, if you have a question, raise your hand, so we'll give the mic to you so that your question can be heard by everybody else, especially the speaker. Any questions?
So offline versus online learning, is offline basically evaluating how the policy will work when you're like not actually running it? Okay.
Yeah. So the question was, I guess it picked up fine on there. Right. So in the offline case, we're using data which we have logged from the deployment of kind of different earlier policies. For instance, if say you have some application, you have an existing solution in place, and now you learn a new policy, we might want to use data from our kind of existing solution to evaluate that new performance. Whereas online, we're just going to run the policy itself and see what happens. Yeah.
Hello. Oh, yeah. Hi. Hello, Dr. Hanna. It's very inspiring. I feel this. I'm not an expert in machine learning, so in my understanding, if it's correct, your research revealed that the data efficiency affect in the training performance, and most importantly, when you sample those data and feed them into the model, it will affect the performance, right? So my question is that, the first question is, does the AI model have some preference to the raw data? Is the sample to be identical distribution with the raw data, or there are some preferences? Like say, if we feed this time we feed the data and we see a big reward, and we want to feed them again.
Yeah. So let me see. I'm not sure I understood the question. Let me see if I can just paraphrase it back right. So it's like, are we trying to? You're talking about like the model fitting the data. So it's not really fitting the data in the same sense that we see in, say, like supervised learning or self-supervised learning in like language models. It's more when we see data that we want to, when we see data which has a good sequence of rewards, you want to kind of push up the probability of that. Mm-hmm. So you see if I say like kind of the data shows me two different actions, one action led to a really good outcome, one to a bad outcome, I don't want to fit the data. I want to kind of ignore that one, like push down the probability of the bad action and increase the probability of the good action.
So there are preferences.
It's kind of baked into the objective function of training.
So actually, so actually, it's not always the case that we want the identical sample from the raw data.
So we're trying to, I guess by real data, we're kind of trying to match in distribution the policy which is producing data for learning is trying to match the distribution of data that we would expect under the current policy.
I see.
The current policy is being updated to prefer taking better actions.
Okay.
So right, we have each policy has two different objectives. One is trying to give a representative data sample, which leads to an accurate gradient estimate. And the other one is just trying to prefer taking better actions, better and better actions over time.
So you're adjusting those distributions gradually?
Yes, yeah.
Yeah. Oh, sorry.
Yeah, thank you for the question. Thank you for your comments.
Any other questions?
Yeah, I just have one quick remark. Your second work feels like a time travel.
Time travel. Okay.
Yeah, so you're making counterfactual, simulations on existing data sets. It's very interesting. I don't know how it works, but it feels very interesting. So my question, actually I have a question on some other topic. So do you use, say you are using a robot cup, are you using different, are training them differently, or just one single algorithm for every robot?
Yeah, good question. So we use the same algorithm. Yeah, I could go a bit more into the training procedure. So we really, again, this is an application where I think we're just scratching the surface, and then we have a lot of new directions which have kind of spun out of our first year of the project. So our first setup, we trained robots individually, so in like a single agent setup. So we had like one robot which is trained in an environment which trains it to be really good at scoring in an empty field. We also trained a robot separately to be a keeper. We trained another robot to be a defender. And then we ended up writing like a lot of what I'd say glue code, but like manually specifying logic to combine these behaviors into one system. So moving forward, what we were almost to the point of doing but didn't quite make for the competition was kind of more full multi-agent learning, where the robots they're learning. It's like two teams of robots that just kind of play against each other, and each team is using a different copy of like the same policy. And so the idea is that as they just kind of iteratively make themselves better, this is a similar way to how AlphaGo was trained to play the game of Go. So that's one direction we're looking at, where then all the agents are using like the same algorithm. They're trained in the same environment, exactly like that. Yeah, thank you.
We have time for 2 quick questions.
Okay, yeah, mine's pretty quick. Do you ever take like inspiration from how humans learn and play soccer? Not necessarily like with the algorithms I'm not necessarily asking about the algorithms, but I played soccer in high school, so I feel like there's stuff to learn from there. Is there?
Yeah, it's interesting. So I guess my goal is to develop general algorithms, and so I try to not think too much about how people would play soccer, because the more kind of domain knowledge we put in, the less likely the algorithm is to be maybe applicable to some other case. So I mean, I think there is a space for that. I think when you're certainly trying to optimize one application, you should put that knowledge in. For instance, I worked with, during my PhD, both my PhD advisor and another one of my lab mates played soccer at a very high level. And they would always have lots of very good insights about how we could be improving for the competition. But I think my research style is to more focus on just general methods, general learning solutions, and try to figure out that knowledge that people have developed there. I do take a lot of inspiration from how I think people are just amazing in how flexible and adaptive we are at decision making. And that's kind of what I would like to recreate with these algorithms.
So we've got a question over here.
Hello. Yeah. So I understand that these are the standard how people run these algorithms. So I was wondering how scalable your methods are when our action space is a tuple. Like we have to select multiple things. So then you can imagine that the action space will become exponential instead of just selecting one action. And so no matter how huge the action space is, it will still remain limited as opposed to having selecting 7 things, so many combinations.
Yeah, that's a great question. The domains we tested on are all continuous control cases where we're testing the agent's output as a vector of real values like motor commands to a robot. With really large discrete action spaces, they're a challenge for many reinforcement learning methods. That case, there's many different kinds of heuristics people have developed for those. So we have not tested yet. We're very interested. One kind of related problem that we're very interested in is using our methods for the kinds of RL done on large language models, which also involves not an exponentially sized, but if you think your model's output is a bunch of different words, maybe your vocab is 50,000 different words, it's much larger than a lot of RL test beds are. So that's one direction we're interested in. I think it's a great question. Be happy to chat more about. Sure, I have some time this afternoon. Be happy to talk more. So, yeah.
We have a last question.
When you're training one policy to train another policy, how often are you updating the second policy compared to the first one?
Yeah, so we're updating the behavior policy which produces data. We've had kind of 2 different iterations of this. Our initial approach here, we updated the behavior policy at every time step. So that's a very rapid update. What actually kind of works better with larger neural networks is to do this a bit slower. So we update the behavior policy more frequently than the policy we're training, but it's like after we've generated some number of full trajectories. Yeah, good question. Thanks.
All right, we thank the speaker very much for your
Yeah, thank you all again for having me. It was really a joy to speak here.